Going to look at a whole heap of different mechanics questions. So the first one I'm starting with is actually a past HSC question. You'll notice it does say extension 1 HSC, but a lot of the more involved motion questions have been moved into extension 2. So I thought this was a good one. So what do we got? It's a ski jump. So a skier is taking off on the ski jump, takes off at O, but then the jump keeps going down below the horizontal there, and then will land at the point P. We didn't have to derive the equations of motion. They gave it to us, which was nice, saves a bit of time. So what's the first part? Basically, they want us to find the Cartesian equation of the path. So eliminate the parameter, and the parameter, of course, is t. So, okay. So x is vt cos theta. T will then be x on v cos theta. Substituting in, now we've got to get it to the form that they want. They've got x tan theta. Oh, yep, that's our second term there, isn't it? The v will cancel with the v and the sine on cos, so that bit's okay. Now, the next bit, yes, reciprocal of cos is sec, so we've pretty much got what they want. Okay, second part. Show that d is equal to this expression. So let me just go back to the question. What was d? That's the distance along the slope there. We have to find that distance there. I'm going to play with the ratio of y over x. So the y value over the x value. Now, the angle for that, y over x, it would be minus pi and 4 because it's going below the horizontal. So basically, I've set up the tan ratio. So playing around with all that, I'm going to end up with t squared. There's t. So I know the time that it lands. We want to find out where it lands. Well, I know d will be the square root of 2x because it was 45 degrees. So that would make it an isosceles right angle triangle. So I can say it's root 2 times the horizontal displacement. And the horizontal displacement was vt cos theta. I've just worked out an expression for t. Subbing that in, we get the result that they're looking for. So let's just recap that. Go back to the picture. Here we go. They want us to find that length d. So what I did is I said, well, I don't know an equation for d. Yeah, okay, I could work one out. It'd be quite messy because I'd be saying the square root of this one squared plus that one squared. And that. So rather than doing that, I took advantage that this was 45 degrees. And so then I knew the hypotenuse would be the square root of 2 times the x. But in order to use the x, I needed to know what t was. And so that's why I started off with this ratio, because I knew that ratio would be the tan of minus pi and 4, and that allowed me to get an expression for t. So let's say a little bit more involved than a standard projectile motion question. But there's more to it. Show that, they could have picked a better letter, couldn't they? Show that the d, the theta, is this expression here. Okay, so we've just worked out d. So we just need to differentiate that with respect to theta. I'm going to play around with the expression there. So expanding out the parentheses, because I notice in their answer, they're referring to 2 theta rather than theta. And sine theta cos theta would be half of sine 2 theta. So if I differentiate that, well, the 2 root 2 v squared on g, that's all just a constant. So differentiate the sine, we get cosine 2 theta. The cos squared, I'd have to use my chain rule for, so bring down the power, etc. We get 2 cos theta sine theta, which is sine 2 theta. And so I come up with the expression they want. Show that d has a maximum value and find the value of theta. Okay, remember there's d. You want to show d has a maximum. That's what they said. We know maximums occur when the first derivative is equal to 0. So you could solve when that's equal to 0 and so on. But what I did instead was I played around with the actual function itself. So there's my expression. So I've turned it into a single trig function. You can use the auxiliary angle idea. I've got a show me if you've got a sine and a cosine of the same angle, you can combine them into one thing. Why did I do that? Because once I've got the trig function, finding a maximum minimum is easy because we know what trig functions do. the maximum of the trig function would be the amplitude, which is 2v squared on g, but in this case I would have to also add on root 2v squared minus g. So I know it'll be a maximum when that is equal to 0, because the cos of 0 is 1. So it'll be pi on 8 is when it happens. And I didn't actually find it. I suppose it didn't say find the maximum value, did it? It just said show that it has a maximum value. All right, so I've showed it has a maximum value. Perhaps a bit of an explanation would have been nice there to say, well, from there, how did you know that was going to have a maximum value? Okay, here's another one. Oh, this is a great question, bird question. It comes from the old Fitzpatrick textbook. So here's the situation. A stone's thrown, there's a bird sitting on the top of the pole, right? So we want to get the bird. However, as soon as I throw it, the bird flies away. But it's a stupid bird. All right? Because it's flying away with a horizontal speed of 10 meters per second. Now, the stone reaches a height, ends up reaching a height double that of the pole, but then the stone comes down and it hits the bird anyway. Okay? So find the horizontal component of the velocity of the stone. Now, the reason I put this here is because I didn't actually use calculus to solve it. I used quadratics. So assuming there's no air resistance, we know it's going to be a parabola. Okay? And so that's what I'm saying. Sometimes, you know about quadratics, certainly in projectile motion questions, because if we're assuming no air resistance, we know it'll be a quadratic. Now, the greatest height then will occur at the vertex of that parabola. We know that'll be the greatest height. So I'm going to let the coordinates of the vertex be 0, 2h, so twice the height of the pole. That means the equation of the parabola will end up being y equals 2h minus kx squared, some constant times x squared. So the blue lines, there's the pole that the bird was sitting on. It's got height h. The bird is flying away. The red line, or the red parabola, is the path of the stone. I throw it up, but then on the way down, bang, it hits the bird. Now, when y is equal to h, h would end up being 2h minus kx squared. Solving that, I now get the x coordinates for the pole, but also when it hits the bird. So plus or minus root h on k. So that point there, that's where the bird was, would be minus root h on kh. And where the stone hits the bird will be root h on kh. So the bird ends up flying a total of 2 root h on k meters at 10 meters per second. Time we know is equal to distance over speed. So I now know that the bird is in flight for 1/5 root h on k. So when y equals 0, so the ground, we get 0 is 2h minus kx squared. So I now know the 2x intercepts of my parabola are plus or minus root 2h on k. Okay, so over there, the left-hand side where I threw it from would be minus root 2h on k, and on the right-hand side would be that one. Well, we're interested in how far the rock travels. So remember, we're trying to find the horizontal component of the rock, the stone, whatever it's called. So it'll travel root 2h on k, but then plus another root h on k. So I can factorise that and I get root h on k outside of root 2 plus 1. Speed equals distance over time. The time of flight of the stone is the same as the time of flight as the bird. Remember, the bird took off as soon as we let the stone go, and then the rock hit the bird. So speed equals distance over time, and we get 5 outside of root 2 plus 1 meters per second. So there's our horizontal velocity of the stone. And remember, from projectile motion, horizontal velocity is always constant. So there's the answer to the question. So I thought, there's a neat little solution to it without actually using calculus. Just use the features of a quadratic. Now, if you want to give a hint to a bird, stupid bird, don't fly away from the stone, fly to the stone, and you would have been fine. Wouldn't have got hit. Hey, dumb bird. Okay. Here's a question from 2003. It was from an Extension 2 paper, but an example of projectile motion, but taking resistance, air resistance, into account as well. And you'll notice that the shape of the path now is no longer parabolic, because the air resistance now having an effect on the shape of the curve. Again, they were nice to us. They gave us the equations of motion, so the acceleration equations, and they made a good point in the test. They said, you are not required to show these, so don't waste time and go and find them. They're giving them to you. They do want us, however, to derive the horizontal velocity. So we've been told horizontally, acceleration was minus k times the horizontal velocity. So we get, well, if I just integrate that as normal, t will end up being minus 1 on k, and it'll be dx on x dot. So basically I've done the separation of the variables all in one go, but I knew the other one was 0 to t, so I just said it was t. The initial condition was it still heads off with a velocity of u cos alpha horizontally. We want to find x dot. So that would be a log function. So there's an expression for t in terms of x, but we want x. Or sorry, in terms of x dot. We want x dot in terms of t. All right, let's rearrange it all then. So t is minus 1 on k. Use our log laws, bring that all into one function there. Multiply out by k, exponentialize, and we get that x dot is u e to the minus kt times the cosine of alpha. Okay, that was the first part of the question. Now, it says verify. In hindsight, I've actually gone and derived it. Because it says verify, all I really needed to do was differentiate that and show that it satisfied the acceleration equation. I've gone and actually calculated it out, so let's do that. T equals minus, and there's our integral, and I end up with minus 1 on k log ky dot plus g. Sub in the limits, playing around with that, but that's t. We want y dot to be the subject. So I kind of went the long way about it, to be honest. It would have been quicker just to differentiate that with respect to time and show that, oh yes, that satisfies the acceleration equation, because they didn't actually say derive it, or they simply said verify that this is the answer. Find the value of t when the particle reaches its maximum height. So mind you, this is now going to save me some time because I already have an expression for our time. And we know maximum height will occur when y dot is equal to 0. So I can just substitute into the expression that I had already found for t and, well, play around with it. There it is. 1 on k log ku sine alpha plus g on g. What is the limiting value of the horizontal displacement of the particle? We've got an expression for the horizontal velocity. So let's rewrite that as dx to t. Now, x will end up being the limit as t approaches infinity of u cos alpha is a constant, but I'm going to have to integrate the e to the minus kt. Well, integrate the exponential, I get minus 1 on k e to the minus kt. As t approaches infinity, well, our e to the minus kt, that's going to approach 0, isn't it? Yes, but then we have plus 1 as well. So our limiting value for the displacement is u cos alpha on k. So when I was putting these together, I'm thinking, gosh, what sorts of things will we look at? And as I tend to do, as you've worked out already, I might have gone a little bit crazy. Further simple harmonic motion. Hooke's law. And that's all to do with springs. So here's a mass on the end of a spring. K is our spring constant. I'm going to assume the resultant force is going down. So mx double dot's my resultant force. And so we'll have some sort of resistance thanks to our spring. They've told me the spring constant is k. The resistance ends up being kx for this problem. So acceleration is minus kx. Acceleration plus k on mx is equal to 0. This is what we call a second order linear constant coefficient differential equation. So when you have a second order linear constant coefficient differential equation, the technique we use, it's okay, don't panic, not in the syllabus, x is equal to e to the lambda t. So if I was to substitute in e to the lambda t, I would end up with lambda squared e to the lambda x plus k on m e to the lambda x, which would give me lambda is plus or minus I times the square root of k on m. Okay, so my solution, remember, is x equals e to the lambda t. So I'm going to have e to the I root k on mt and e to the minus I root k on mt and multiples of those. That would be the logical solution to this problem. And you could go and differentiate a couple of times and prove that it does indeed work. Remember, e to the iota theta, I can rewrite as cis theta. So I get, so x will now be a plus b cos of root k on mt plus plus a minus b sine root k on mt. Now, we know that when t equals 0, x is equal to 0. We're just saying, okay, it starts from this point. So therefore, a plus b is equal to 0. So thus, x must equal some constant. Yeah, okay, that constant is whatever a minus b would be. C sine root k on mt. Hooke's law. As I say, not in the course. But, let's take this even further. A spring, so what we're saying, a spring is behaving like a sine curve. If you think of a spring, you pull it down, what does it do? It goes up and down, up and down, up and down. That makes sense. But if I wanted to use that spring as a shock absorber, then it wouldn't really be good. Imagine you're in your car and it's just acting like a sine curve. You'll be driving along and the car will be going up and down, up and down, up and down. Not what you want. You need to add what's called a damper. So now the problem looks like this, and my resultant force will be going this way. Okay, we will have one resistance called Kx, another resistance which will now be C, and that will be times the velocity of x. So now my equation is mx double dot is minus cx dot minus kx. Well, to make life a little bit easier, we'll just let m equal k equal c equal 1. It'll make the maths a little bit nicer. So there's another second order differential equation. We'll try e to the lambda t for this one. So lambda squared plus lambda plus 1 will end up equaling 0. So lambda this time will be minus 1 plus or minus I root 3 on 2. X equals a e to the power of minus 1 plus I root 3 on 2t plus b e to the minus 1 minus I root 3 on 2t. So there's x. I can factorise out the e to the minus half t. Then I can play around with the e to the iota theta, make that cis theta. Now, when t equals 0, x is equal to 0, therefore a plus b is equal to 0, similar to what just happened in the last one. But now we get a much more interesting function. It's not just a sine function, it's a sine function multiplied by an exponential function. So now our curve looks something like this, which that's what you want with a shock absorber. It'll hit the bump and you'll go up, but then you want that to come back down to a nice level point as you go along. And so there's the equation for a shock absorber. Well, I just thought that's a nice way to finish off Extension 2 Maths, because that is the last bit of theory. So do not panic about those last two. All right? Do not panic.